Sequence alignment. For the remainder of this chapter, we consider two further dynamic programming algorithms that each have a wide range of applications. In the next two sections, we discuss sequence alignment, a fundamental problem that arises in comparing strings. Following this, we turn to the problem of computing shortest paths in graphs when edges have costs that may be negative. The problem: dictionaries on the web seem to get more and more useful. Often it seems easier to put up a bookmarked online dictionary than to get a physical dictionary down from the bookshelf. And many online dictionaries offer functions that you can't get from a printed one. If you're looking for a definition and type in a word it doesn't contain, say, occurrence with E replaced by A, it will come back and ask, perhaps you mean occurrence? How does it do this? Did you truly know what you had in mind? Let's defer the second question to a different book and think a little about the first one. To decide what you probably meant, it would be natural to search the dictionary for the word most similar to the one you typed in. To do this, we have to answer the question, how should we define a similarity between two words or streams? Intuitively, we'd like to say that occurrence with E replaced by A and the truly occurrence, this word, are similar because we can make the two words identical if we add a C to the first word and change the A to an E. Since neither of these changes seems so large, we conclude that the words are quite similar. To put it another way, we can nearly line up the two words letter by letter. The hyphen indicates a gap where we had to add a letter to the second word to get it to line up with the first. Moreover, our lining up is not perfect in that an E is lined up with an A. So here's the lineup. O line up with O, hyphen line up with C, C line up with C, U line up with U, R line up with R line up with R, A line up with E, N line up with N, C line up with C, E line up with C. E line up with E, sorry. So we want a model in which similarity is determined roughly by the number of gaps and the mismatches we incur when we line up the two words. Of course, there are many possible ways to line up the two words. For example, we could have written O line up with O, hyphen line up with the first C, C line up with the second C, U line up with U, R line up with R, another R line up with another R, hyphen line up with E, A line up with hyphen, N line up with N, C line up with C, and E line up with E, which involves three gaps and no mismatches. Which is better, one gap and one mismatch, or three gaps and no mismatches? This discussion has been made easier because we know roughly what the correspondence ought to look like when the two streams don't look like English words. For example, like A, B, 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 A, B, 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 A, B, and A, B, A, B, A, B, 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 A, B. It may take a little work to decide whether they can be lined up nicely or not. Actually, there's an error in this page. Did you find it? Dictionary interfaces and spell checkers are not the most computationally intensive application for this type of problem. In fact, determining similarities among streams is one of the central computational problems facing molecular biologists today. Streams arise very naturally in biology. An organism's genome, its full set of genetic material, is divided up into giant linear DNA molecules known as chromosomes, each of which serves conceptually as a one-dimensional chemical storage device. Indeed, it does not obscure reality very much to think of it as an enormous linear tape containing a stream over the alphabet, the set ACGT. A stream of symbols encodes the instructions for building protein molecules using a chemical mechanism for reading portions of the chromosome. A cell can construct the proteins that in turn control its metabolism. Why is similarity important in this picture? To a first approximation, the sequence of symbols in an organism's genome can be viewed as determining the properties of the organism. So suppose we have two strains of bacteria, X and Y, which are closely related evolutionarily. Suppose further that we've determined that a certain substrain in the DNA of X codes for a certain kind of toxin. Then, if we discover a very similar substrain in the DNA of Y, we might be able to hypothesize, before performing any experiments at all, that this portion of the DNA in Y codes for a similar kind of toxin. This use of computation to guide decisions about biological experiments is one of the hallmarks of the field of computational biology. All this leaves us with the same question we asked initially. While typing badly spelled words into our online dictionary, how should we define the notion of a similarity between two streams? In the early 1970s, the two molecular biologists, Needleman and Watch, proposed a definition of similarity, which basically unchanged has become the standard definition in use today. Its position as a standard was reinforced by its simplicity and intuitive appeal, as well as through its independent discovery by several other researchers around the same time. Moreover, this definition of similarity can, with an efficient dynamic programming algorithm, to compute it. In this way, the paradigm of dynamic programming was independently discovered by biologists some 20 years after mathematicians and computer scientists first articulated it. The definition is motivated by the considerations we discussed above, and in particular by the notion of lining up two streams. Suppose we are given two streams X and Y, where X consists of the sequence of symbols x1, x2, x3, and so on to xm, and Y consists of the sequence of symbols y1, y2, y3 until yn. Consider the sets 1 to 3 until m, and the set 1 to 3 until n as representing the different positions in the streams x and y, and consider a matching of these sets. We call that a matching is a set of ordered pairs with the property that each item occurs in at most one pair. We say that a matching M of these two sets is an alignment if there are no crossing pairs. If the pair ij and the pair I prime, j prime in M, and I is less than I prime, then j is less than j prime. Intuitively, an alignment gives a way of lining up the two streams by telling us which pairs of positions will be lined up with one another. Thus, for example, STOP hyphen and hyphen TOPS correspond to the alignment 2 1, 3 2, and 4 3. Our definition of similarity will be based on finding the optimal alignment between X and Y according to the following criteria. Suppose M is a given alignment between X and Y. First, there is a parameter delta greater than 0 that defines a gap penalty. For each position of x or y that is not matched in M, it is a gap. We incur a cost of delta. Second, for each pair of letters P, Q in our alphabet, there is a mismatch cost of alpha PQ for lining up P with Q. Thus, for each pair ij in M, we pay the appropriate mismatch cost, alpha xiyj, for lining up xi with yj. One generally assumes that alpha pp is equals to 0 for each letter P. There is no mismatch cost to line up a letter with another copy of itself, although this will not be necessary in anything that follows. The cost of M is the sum of its gap and mismatch costs, and we seek an alignment of minimum cost. The process of minimizing this cost is often referred to as a sequence alignment in the biology literature. The quantities delta and the set alpha pq are external parameters that must be plugged into software for sequence alignment. Indeed, a lot of work goes into choosing the settings for these parameters. From our point of view, in designing an algorithm for sequence alignment, we will take them as given. To go back to our first example, notice how these parameters determine which alignment of occurrence with C, single C, and E replaced by A, and the real-world occurrence we should prefer. The first is strictly better if and only if delta plus alpha AE is less than 3 delta. Designing the algorithm. We now have a concrete numerical definition for the similarity between streams x and y. It is the minimum cost of an alignment between x and y. The lower this cost, the more similar we declare the streams to be. We now turn to the problem of computing this minimum cost and an optimal alignment that yields it for a given pair of streams x and y. One of the approaches we could try for this problem is dynamic programming, and we are motivated by the following basic dichotomy. In the optimal alignment M, either Mn is in M or Mn is not in M. That is, either the last symbols in the two streams are matched to each other, or they aren't. By itself, this fact would be too weak to provide us with a dynamic programming solution. Suppose, however, that we compound it with the following basic fact. 6.14. Let M be any alignment of x and y. If Mn is not in M, then either the mth position of x or the nth position of y is not matched in M. Proof. Suppose by way of contradiction that Mn is not in M, and there are numbers I which is less than M and j which is less than n, so that mj is in M and in is in M. But this contradicts our definition of alignment. We have in, mj in M with I less than n, but n is greater than I. So here's in and mj cross. There is an equivalent way to write 6.14 that exposes three alternative possibilities and leads directly to the formulation of a recurrence. 6.15. In an optimal alignment M, at least one of the following is true. 1. Mn is in M. Or 2. The mth position of x is not matched. Or 3. The nth position of y is not matched. Now let obt of ij denote the minimum cost of an alignment between x1, x2, x3 until xi, and y1, y2, y3 until yj. If case 1 of 6.15 holds, we pay alpha xm yn, and then align x1, x2, and so on until xm minus 1, as well as possible with y1, y2, y3 until yn minus 1. We get obt of mn equals to alpha xm yn plus OBT of n minus 1 n minus 1. If case 2 holds, we pay a gap cost of delta since the mth position of x is not matched, and then we align x1, x2, x3, and so on until xn minus 1, as well as possible with y1, y2, y3 until yn. In this way, we get OBT of mn is equals to delta plus OBT of n minus 1 n. Similarly, if case 3 holds, we get OBT of mn equals to delta plus OBT of n minus 1. Using the same argument for the subproblem of finding the minimal cost alignment between x1, x2, x3 until xi, and y1, y2, y3 until yj, we get the following fact. 6.16. The minimal alignment cost satisfies the following recurrence for I which is greater than or equal to 1 and j which is greater than or equal to 1. That is, OBT of ij is equals to the minima chosen among alpha xi yj plus OBT of I minus 1 j minus 1 delta and delta plus OBT of I minus 1 j and delta plus OBT of I j minus 1. Moreover, Ij is an optimal alignment amp for the subproblem if and only if the minima is achieved by the first of these values, these three values. We have maneuvered ourselves into a position where the dynamic programming algorithm has become clear. We build up the values of OBT of Ij using the recurrence in 6.16. There are only big O of Mn subproblems, and OBT of Mn is the value we are seeking. We now specify the algorithm to compute the value of the optimal alignment for purpose of initialization. We note that OBT of I0 is equals to OBT of 0i, which is equals to I delta for OI, since the only way to line up an I letter word with a 0 letter word is to use I gaps. So here's the algorithm. Alignment of x and y. We set up array M, which is a two-dimensional array with a row starting from 0, 1, 2, 3 until m, and a column starting from 0, 1, 2, 3 until n. We initialize A of I0 is equals to I delta for each I, and we initialize the A of 0j equals to j delta for each j. For j starting from 1, 2, 3 until n, there is another for loop inside of it. That is, for I starting from 1, 2, 3 until m, we use the recurrence 6.16 to compute A of ij. Finally, after we finish the loops, we return A of mn. As in previous dynamic programming algorithms, we can trace back through the array A using the second part of fact 6.16 to construct the alignment itself. Analyzing the algorithm. The correctness of the algorithm follows directly from 6.16. The running time is big O of mn, since the array A has big O of mn entries, and at worst we spend constant time on each. There is an appealing pictorial way in which people think about this sequence alignment algorithm. Suppose we build a two-dimensional m by n grid graph gxy with the rows labeled by symbols in the string x and the columns labeled by symbols in y, and directed edges as in figure 6.17. We number the rows from 0 to m and the columns from 0 to n. We denote the node in the ith row and the jth column by the label ij. We put costs on the edges of gxy. The cost of each horizontal and the vertical edge is delta, and the cost of the diagonal edge from I-1, j-1 to ij is alpha xi yj. The purpose of this picture now emerges. The recurrence in 6.16 for OBT of ij is precisely the recurrence one gets from the minima cost path in gxy from 0, 0 to ij. Thus, we can show that at 6.17, let f of ij denote the minimal cost of a path from 0, 0 to ij in gxy. Then for all ij, we have f of ij is equals to obt of ij. Proof. We can easily prove this by induction on I plus j. When I plus j is equals to 0, we have I equals to j equals to 0, and indeed f of ij is equals to obt of ij, which is equals to 0. We now consider arbitrary values of I and j, and suppose that the statement is true for all pairs I prime j prime with I prime plus j prime, which is less than I plus j. The last edge on the shortest path to ij is either from I minus 1 j minus 1 or I minus 1 j or I j minus 1. Thus, we have f of ij is equals to minima chosen among alpha xi yj plus f of I minus 1 j minus 1 or delta plus f of I minus 1 j or delta plus f of I j minus 1, which is equals to the minima taken among alpha xi yj plus obt of I minus 1 j minus 1 or delta plus obt of I minus 1 j or delta plus obt of I j minus 1, which is equals to obt of ij. Where we pass from the first line to the second using the induction hypothesis, and we pass from the second to the third using 6.16, and we pass from the second to the value of using the optimal 6.16 alignment is the length of the shortest path in gxy from 0, 0 to mn. We'll call any path in gxy from 0, 0 to mn a corner-to-corner path. Moreover, the diagonal edges used in the shortest path corresponded precisely to the pairs used in the minimal cost alignment. These connections to the shortest path problem in the graph gxy do not directly yield an improvement in the running time for the sequence alignment problem. However, they do help one's intuition for the problem and have been useful in suggesting alignments for more complex variations on sequence alignment. For an example, figure 6.18 shows the value of the shortest path from 0, 0 to each node ij for the problem of aligning the words and NAME and NAME. For the purpose of this example, we assume that delta is equal to 2. We assume that matching a vowel with a different vowel or vowel consonant with a different consonant or a constant with a different constant costs matching 1, a vowel and while matching a vowel with each other costs 3. For each cell in the table representing the corresponding node, the arrow indicates the last step of the shortest path leading to that node. In other words, the way that the minimum is achieved in 6.16. Thus, by following arrows backwards from node 4, 4, we can trace back to constructed the alignment.